12 people walked on the surface of the moon during the Apollo program. Every one of them was wearing a life support system, a human-sized life support system, because beneath the white exterior were layers designed to do something extraordinary. To keep a human alive in an environment where the human body could not survive for more than a moment. You'd assume the biggest danger on the moon was the cold. It wasn't. The real problem was the opposite. The human body constantly produces heat. On Earth, sweat, moving air, and evaporation carry that heat away. Inside a spacesuit on the moon, ventilation could move air around an astronaut, but it couldn't carry enough heat away into the vacuum of space. Directly against the skin, astronauts wore a thin garment woven with nearly 300 feet of tiny plastic tubing. Water circulated through those tubes, absorbing heat from the body. But that heat had to go somewhere. The solution was in the backpack. So the water was carried back to the backpack, where it passed through a component exposed to the vacuum of space. There, the heat could be released before the cooled water returned to the suit. But the astronaut didn't just need cooling. He also needed air to breathe and a way to circulate it around his body. The suit's ventilation system helped move that air through the helmet and around the astronaut, while also helping control moisture and heat inside the suit. Air could keep the astronaut's environment circulating, but water could carry the body's heat far more efficiently. And underneath all of this was an even more fundamental requirement: pressure. The Apollo suit was pressurized to about 3.7 pounds per square inch, roughly a quarter of what you're experiencing at sea level right now. That wasn't a limitation. It was a choice. Engineers could have used a higher pressure, but every extra bit of pressure would have made the suit harder to move, and mobility mattered just as much as survival. So they chose a lower pressure that could still provide the protection the astronaut needed, while making the suit more workable. Even so, just above the cooling garment was a pressurized bladder, essentially a flexible balloon filled with oxygen. And every balloon wants to become a sphere. No elbows, no knees, no bent fingers. Just the simplest shape physics can give it. So engineers added another layer, a restraint layer, tailored to the astronaut's body, holding that balloon in the shape of a human. Pressure kept him alive. The restraint layer kept that pressure from turning the suit into a balloon. But now they had another problem. How do you move inside it? Even with the relatively low pressure inside, the suit was still a pressurized environment. So how does an astronaut bend his arm at all inside a pressurized suit? The answer was built directly into the joints. Specially shaped sections called convolutes allowed the elbows, knees, shoulders, and hips to bend without simply fighting against the pressure inside the suit. Inside the convolutes, small cable and pulley systems helped control the movement of the joints, reducing the suit's tendency to straighten as the astronaut bent it. The gloves were especially demanding. A pressurized glove wants to pop open like a balloon, but an astronaut needed to do the exact opposite. He had to close his fingers, turn switches, pick things up, operate instruments. Every one of those movements meant fighting the pressure inside the glove. That's why the gloves were carefully fitted to each astronaut's hands, with the geometry designed to preserve as much dexterity as possible. But the pressure glove couldn't do all of that on its own. It had to remain flexible enough for the astronaut to work, while also surviving the abrasive lunar environment. So over the pressurized glove, astronauts wore a separate protective outer glove. And then there was the heat. The astronaut was producing it from inside. The sun was heating the suit from outside. So the suit needed layers that could slow heat moving in either direction. Multiple layers of insulation, separated by thin spacers, helped create that barrier. But the suit still had to survive the moon itself. Everything so far was protecting the astronaut from things he couldn't see. The outer layers had to protect him from the moon itself. One of the most important materials was beta cloth, a fiberglass-based fabric that formed the suit's outer protective covering. And this is also why the suit was white, to reflect as much of the sun's radiation as possible. But there was another problem at the astronauts' feet. Lunar dust was sharp, abrasive, and extremely fine, a particularly bad combination for the suit's joints, seals, and moving parts. That's why the astronauts wore separate lunar overboots over the suit's feet. Like the overgloves, the overboots weren't part of the pressurized garment. They were an additional protective layer, keeping the most abrasive material on the moon away from the suit itself. There was another surprisingly complicated part of the suit, the zipper. The Apollo suit had a pressure-sealing zipper running down the astronaut's back, from the upper back through the crotch. But it wasn't just one zipper, it was actually 3 layers. Brass zipper, rubber, brass zipper. When the suit was pressurized, the rubber layer expanded between the 2 zippers, creating an airtight seal. So the zipper wasn't simply there to let the astronaut get into the suit, it was part of the pressure system itself. And the suit had to keep that seal intact while the astronaut moved, walked, and worked on the moon. But the moon had another problem. There was no atmosphere to filter sunlight. So looking toward the sun wasn't simply uncomfortable, it could damage your vision. The solution was one of the strangest details on the entire suit: gold. The helmet's outer visor was coated with an extremely thin layer of gold. It was essentially a wearable solar filter, reflecting away dangerous levels of sunlight while still allowing the astronaut to see through it. A tiny layer of gold, doing an enormous job. But none of these layers could keep an astronaut alive on their own. And this brings us back to the machine that had to keep the entire system running: the portable life support system. The PLSS, or the backpack, was the part of the suit responsible for supplying everything the astronaut needed to stay alive. Air to breathe, a way to deal with the carbon dioxide he exhaled, cooling, and the power and communications needed to keep him connected to the spacecraft. On Earth, the PLSS weighed about 84 pounds. On the moon, with 1/6 of Earth's gravity, it felt like roughly 14. It was, in effect, the engine behind everything we just discussed. And that's what made the Apollo suit so extraordinary. Every part of it, from the smallest layer to the life support system on the astronaut's back, existed for the same reason: to keep a human being alive in a place where humans were never meant to live. 21 functional layers, all working together for one purpose: keeping one human being alive on the moon.